these reaction predictions. The first one here says solid, and that's why we read these, because it says solid ammonium chloride. Let me get my pen out here. So again, I know ammonium chloride is soluble in water, but it was added as a solid, and so ammonium chloride would be a solid. Is added to, see, you can see we have words here that matter. A solution of potassium hydroxide. So that's KOH, that is aqueous. Okay. Then it says, what am I make? So this is a double replacement reaction. So the ammonium and the potassium will exchange partners. When that occurs, you get ammonium hydroxide. Well, unfortunately, you might not remember this, but when we get into Unit 4, you're going to find ammonium hydroxide is highly unstable. It actually breaks down to ammonia and water. Whether you choose H2O or HOH, it doesn't matter. But those are my other products, the products instead of ammonium hydroxide. Oh, and then the K goes with the NH4Cl, and so we have KCl. The KOH added water. Now, what's ammonia? That is a gas, right? Water is a liquid. KCl, soluble or insoluble? Now, all alkaline metals, we'll start with that one because that's the first rule. All alkaline metal salts are soluble. Page 100, if you want to remember this. So that is soluble. So now what you do is you take anything that is soluble and break it apart. The ammonium chloride does not break down. The potassium hydroxide does. Ammonia is obviously a gas, so that stays. Water can stay. The K breaks down with the Cl. Again, if it's soluble, it breaks down to its component parts. Any spectators there? Things that show up exactly the same on both sides? Potassiums. And so then I just rewrite what's left over. Easy enough? And the question asks the verifying question after it says, identify any gases that are produced? Seems to me like there's only one of them. Right? Okay. So any other questions on the first reaction? Not too bad. Okay, number 2. A solution of hydrogen peroxide is heated. Okay. Hydrogen peroxide is H2O2. So H2O2 doesn't break down. It's an organic substance, so it just stays as is. It's a decomposition anyway, so nothing breaks apart in a decomposition. So H2O2 goes to, remember this, H2O and O2. Now you just have to balance it. That's all you have to do. Just balance it. Ooh, here's a tricky one. The identifying question would cause me to have to look some things up here. Identify what is being oxidized and reduced. What is being oxidized and reduced? Now, let me give you the definitions of these because maybe that will help. So when we do oxidation and reduction, which will be in chapter 3, I will give you a little mnemonic, I guess they call it, to remember by. One will be the term oil rig. Now, why do I say oil rig? Because oil means oxidation is the loss. Oil. Reduction is the gain of electrons. Oxidation is the loss and reduction is the gain of electrons. So if something is oxidized, that means it is losing electrons. If something is reduced, reduction is the gain, it gains electrons. That's what that means. Now, maybe you're somebody and you're like, hey, that's not very environmentally friendly to be talking about oil rigs. I am offended. Okay, let's talk about something else. Another one for those of us who are maybe more pet friendly. I know that Carol Baskin's husband was eaten by her tigers, but maybe you have lions that you like to think about. Leo the lion says grr. Loss of electrons is oxidation. Gain of electrons is reduction. How about that? Whichever one suits you better, grab onto it. I can tell you this. I never learned Leo the lion says grr till later, but it doesn't matter. I learned oil rig. I didn't even learn it in high school. I learned it in college, and I still use it all the time. Because it's easy to sometimes forget. Like oxidation used to be something that took on oxygen. So it was oxidized, it took on oxygen. Reduced meant that you heated it and oxygen left. And then we realized that what was really happening involved things that didn't have oxygen in them. So now what we do is we look at electrons. So even in my mind, sometimes I'll be doing something where I'm writing it down, and I might forget in my mind, oxidation is the loss. So I'll go, well, oxidation is the loss, reduction is the gain. It's a very simple one. Well, it's easy to do the name, or at least the definitions, but how do I use the information? Here's how I do that. I take H2O2. It says oxidation, oxidized. We're going to look at charge. So what is the charge of a hydrogen atom? Or let's say ion. It's +1, right? Hydrogen +1. What is the charge of oxygen in peroxide? Because there are two hydrogens, that makes the hydrogen overall a +2. Because it's +1 for each. So what's the charge of an oxygen in peroxide? -1. Remember this? O2 -2 is peroxide. Each O is a -1. Okay. What does that go to? We said H2O. Which remember, again, you have to balance it. What's the charge of H? Plus. What's the charge of O? -2. Ooh, tricky. Okay. And then here, O2. What is the charge of oxygen gas? No charge. 0. What Gabe gets when he doesn't turn things in, right? So let's see here. Did the hydrogen change at all? Did the oxygen change at all? Yeah. You see, in this one, it got more negative, right? So if you're a negative person and you tend to have more negative people in your life, you tend to get even more negative, right? So if you have a -1, to become even more negative, what do you do with electrons? You gain them. You get more of them. It's reduced. It's gaining electrons. Now look at this oxygen. I'll do it again. When you go from -1 to 0, you're becoming more positive, right? So you're getting more positive people in your life. The people who took AP chemistry, those people who think like a proton. And so when you are getting more positive, we're not talking about, you can't gain protons because then you become something different. So how do you get more positive? You lose electrons. So this tells me that oxygen is both reduced and oxidized. Yep. 2 down, a few more to go. Ammonia gas is bubbled into a solution of hydrofluoric acid. Ooh, what's ammonia gas? NH3. It's bubbled into a solution of hydrofluoric acid. Any idea what that is? H something. Hydro means it's a binary acid. So it means it's hydrogen and one other element. That means H and F.
I always forget this info.
Well, yeah, that would be the element down there, number 114, which we'll never use. So it's HF. So what do I get with this? Ooh. It is not a single replacement reaction. This is a synthesis reaction. So we combine everything. And when I combine the NH3 and the HF, I get NH4Cl. Oh, F. NH4F. Sorry. Right, I get exactly what I started with. Yeah, it's one of those weird reactions. You actually make something different. You like that? Yeah, this is a real cool reaction. You start with fluorine and you end with chlorine. Yeah. Yeah, well, you really got to learn this reaction. Boy, this is a real odd one. Yeah. Becomes very difficult to balance. How many fluorines are on one side? One. How many on the other side? There aren't any. Oh, what do you do? Next one. Let's move on. Now, here's the things to think about, a couple of them. First off, what is ammonia? Gas. Now, HF is an acid. Now, with it being an acid, we have to look at strong acids versus weak acids. Here are the strong acids, and these are all in that book as well. Hydrochloric, okay, hydrobromic, hydroiodic, sulfuric, nitric, perchloric, and chloric acid. Those are the 7. In any of those did I mention hydrofluoric? No. Hydrochloric, hydrobromic, hydrochloric, hydrobromic, hydroiodic, sulfuric, nitric, perchloric, and chloric acid. None of those are hydrofluoric. Hydrofluoric acid is a weak acid, which means it does not break down. Okay. It's a solution of, so there is water. Ammonium. All ammonium and alkali metal compounds are soluble. That will be the only thing that changes Yeah, you just got to memorize, that's all. Do you remember, well, maybe not remember, because you may not have even had this. Any people here in Latin? Ah, see, Denny has. Do they ever go over the word what a conjugate is? Or at least what conjugate means? Did they ever talk to you about that? Or like what they use it sometimes to put up to like when they use it to identify things? I don't know. That's what I'm asking you. I don't know. Well, maybe and what do they use it for in math? Conjugate means to break apart, doesn't that? Yeah, that's not what we mean here. So when you talk about a conjugate acid-base pair, this is what this means. In Latin terms, they often will use this to describe a married couple. Is that the conjugate pair are the two that go together. They're not the same, but they're a pair. They're like each other. And so when we talk about a conjugate acid-base pair, these are two things that are very similar. They look like each other, except one is an acid and one is a base. And so what a conjugate acid-base pair might be is that this is an acid, and when something happens to it, it becomes a base. And let me give you an example. What is ammonia? Acid or base? Base. This is a base. What is HF? Acid. Now let's go to the products. Which one looks like ammonia? Right? This one. Doesn't this look like this? Right? So these are a pair. They're very similar compounds. What's the only thing that happened to ammonia to make it NH4? It gained an extra H. When it has the NH3, it's a base, but when it gains an H, it becomes the conjugate acid. That's the acid. This is the conjugate acid-base pair. So let's look at the other one. What happened to the HF? And again, I'm not expecting us to memorize this. Here's the point of us doing this. We start to see these things now, and we see them now, and we see them maybe in 2 or 3 weeks, and then we see it in a couple other weeks, and then we see it in a couple other weeks. It starts to plant seeds, and then whenever we get to acids and bases, you'll say, oh, I remember seeing that, and then you'll know why it happens. So what does F minus look like? HF, right? And so the only difference between HF and F minus is it, instead of gaining an H, it loses an H. You'll notice when it gained an H, it became an acid, but when it lost an H, it became a base. So you have two conjugate acid-base pairs, you pick one of them, doesn't matter. So is it NH3 and NH4 plus? It says just identify one, doesn't it? It says A, there are two of them. Let's pick one of them. Okay. A piece of aluminum metal, what's that? That's just Al. And remember, aluminum metal, if I look on the periodic table, it's salt. Piece of aluminum metal is added to a solution of, oh, here's one of my favorites, silver nitrate. Silver nitrate. Boy, I'm a little worried about chemistry class. He's old. He has some concerning health conditions, being obese and those kinds of things. Not morbidly, but slightly obese. I hope he's okay. I haven't heard from him in a while. I wonder if he'll this year have to send us a message from the North Polar. That would be odd. You never know. First year we might be in the same room together. Aluminum, oh, this is an easy one. This is what type of reaction? Single replacement, right? So when this replaces, we get the Al with the NO3, and Al is a +3, right? And then now the silver gets kicked out, like Gabe probably in most of his Zoom meetings. And so then when I balance it, there's probably like a 3 here and a 3 here. And as I do this, all nitrates are soluble, right? So this is aqueous. This is aqueous. So that my aluminum plus my 3 silvers goes to my aluminum and my 3 silvers. Right? So when it says what's the change in oxidation number for that last one there, the oxidation number is just its charge. Again, when you, my physics friends are probably very mad at me. Mr. Campbell would probably send me nasty text messages. Dr. Kohler would probably do the same on our text chain. But I know we're buds. But whenever I look at this, if I say charge, in physics they'll say, no, it's not. There's a real charge. There's like a number, and it's in coulombs. And I know there is, but for our purposes, it doesn't matter. Just like they don't care about sig figs, right? So when we look at this, what's the charge of aluminum that you start with? 0. And what's the charge at the end? +2, right? So any questions on those first 4? Okay. Next.
Mr. Atanzio,
Yep. Yes, Jakob.
are we going to need to know any of the
Yeah.
metal reactivities or non-metal reactivities?
Well, yes and no. Let me try to explain. Yes, but all of these reactions will occur. Is that okay? Does that make sense?
Yeah.
So when we get to that point, yes. Okay. Pure solid phosphorus. Now I know this matters to you, whether it was the white form, the red form, the yellow form, or the black form. It is the white form. I'm sure that matters a lot. Pure solid phosphorus is burned in air. Ooh, very interesting. So phosphorus, if you recall, is P4. Anna says, I remember that. Of course. When I was doing all of my fun sheets over again this summer, I remember doing that. Anna told me that she did every fun sheet 4 times during the pandemic. She said, most of my friends watched Netflix. I did fun sheets.
You know what's funny last year was seeing the number of views on the YouTube videos just go down.
Yes, they did go down. How is it that there were not many views on there? Yeah.
It was like 50 over 50, and then all of a sudden it'd be like 50.
I assumed that people were having watch parties. That's what I assumed.
And the last couple, they were only like 10, 15.
How's that possible? Those were awesome videos. They were very informative. I put them on my son's YouTube channel, and he was amazed that he had 500 people view one of his videos.
Oh yeah, I'm watching his Fortnite videos.
I was like, oh. He's gotten very, very good at it. Very good. He's really good now. Did you? Yeah, he's really good. Now he does, like, before he was like, okay, now he wins almost every game he plays in. He's gotten good. And now he doesn't even try to like win. He just tries to like get a whole bunch of kills. He got 35 in a game. I was like, that's a lot, isn't it? He's like, yeah.
That's over a third of the
Yeah.
people in the.
Or he'll go in and he'll try just to shoot people like with a trick shot. I'm like, whatever, dude. Whatever. I know. I'm sure one day he'll be a famous person that sits on my couch and plays video games. Yeah, I doubt it. Well, I will say that he went out one day and some kid recognized him.
Are you serious?
Well, someone was like, "Hey, aren't you Jacko Mighty?" And he was like, "I was like, oh my god, did you give that kid $5? There's no way that kid knows who you are." His videos are off. Okay, P4. P4. Let's see here. Phase up. Yeah, Phase Clan. Whatever that means. He knows it. He has a Phase Clan jersey.
Did he go like this?
I don't know. He's really into someone now called Lanky Box. I don't know what that means. It's a Caucasian guy and an Asian guy, and they just like do stupid stuff. I don't know. And they laugh all the time. That's all they do is laugh at each other. Whatever. They remind me of Jacob and Dietrich. Just kidding. They are odd. They just laugh. They just laugh. They cut a hole in pizza and put on his head. He's like,
I was like watching YouTube videos all the time.
he comes in and he sits on the couch and he turns on YouTube.
Yeah.
That's weird. This is so when I look at this reaction, this is a synthesis reaction. Now, as you look at it, you're like, okay, okay, so, PO, OP, what does this do? Well, this gives me an oxide of phosphorus. Now, when you look at phosphorus, there are several charges it can have. One of them being, so if it's the first element, it can be, it can have charges of +5, it can be +3. Remember how like arsenic can be +3 or +5? And also can have -3 and so forth. As the first one, it has two charges, either +3 or +5, and oxygen can be a -2. And so P2O5 would be a good option, except it dimerizes to make P4O10.
I totally know.
Well, it means that when you see P2O5, right, because of +5 -2, it means that that substance actually finds another one just like it, and they pair up and they make P4O10. Now all you gotta do is balance it, which I think one coefficient will do that. Elemental phosphorus, as prepared artificially, exists in several isotopes. What is at least one other allotrope? I say isotopes, I'm an allotrope. What is one other allotrope other than white phosphorus? I mentioned a whole bunch of them. Matches have one type. If you think about the end of a match head, when you are in the bathroom lighting up, all right, you Joule, so you don't even need those. But whatever, when you look at the tip of a match, the reason it has that color, hint, hint, is because it has that kind of phosphorus. And then I mentioned the other ones. Right? Okay. Solutions of sodium chromate, so Na2CrO4. Solutions of sodium chromate and lead-2 nitrate, so lead-2 nitrate, are mixed. Yes. So this is what type of reaction? Double replacement, right? So when I mix these around, I get and okay. So now I would probably need like a 2 here maybe to balance this. Solutions of, these are aqueous, right? So I would end up with my 2 Na pluses, my CrO4 minus 2, my Pb plus 2, 2 nitrates, two NAs, my 2 nitrates, and then PbCrO4 is a precipitate. If you went through this and you said, uh-oh, everything is soluble, then you're wrong. Every one of these reactions must occur. You notice any spectators here? The 2 NAs and the 2 NO3s. And so you write what's left over, and that would be my net ionic equation. Oxidation number of chromium in chromate. Is that what it says? I saw? Yeah. So CrO4 minus 2. Well, we know oxygen has what charge? Minus 2, right? So chromium, I don't know, right? Plus, I have 4 oxygens, and the overall charge must be a -2. And that should give me my charge of just the chromium. Now, when you look at it on the periodic table, hopefully that matches up with the Roman numeral above it, or at least that should be one of its charges. Now, I know chromium can be +2, +3, but we can also have that one too. Lithium is burned in air. Lithium, Li. Burned in air means you get what other reactant? Oxygen. Li plus 1, O minus 2, Li2O. Now all you have to do is balance it. When water is added to the product, so when water is added to the product, what new compound is formed? Well, let's think of this. This goes back to our synthesis reactions, and it's actually the reverse of a decomposition. Metal oxides in water, remember what they make? Hydroxide. See that? Really smart. That's right. Reading Adam's mind. He's at home thinking of that. Moulton knew that. Solid ammonium carbonate is Eden. Now this looks a lot more intimidating than what it really is. This is a decomposition. Can you think of any products that might be formed? And they're all very common. NH3, CO2, water. Now all you have to do is balance it. And then it just asks what type of reaction this is. This is just a decomposition, right? So are there any questions about that one? Yeah.
Why isn't the ones that are burned there?
Sometimes people will consider them that, but most often when we have a combustion, we have to have a hydrocarbon as well. So usually we consider a combustion having a hydrocarbon with that burning.